So today we study another problem on graphs, which is called the single source shortest path problem. Now for this problem, what we are looking for is this: given a graph G with weights, with edge weights, and a source vertex S which belongs to V, find shortest paths to all other vertices in V. That is the problem. So this is called single source shortest path problem. So let me just take an example here. So suppose this is the graph. So suppose this is the source vertex. The edge weights are 4.5, 6.1, 2.1, 3.2, 2.2, 9.0, 5.7, 3.2. I'm just choosing one arbitrary graph. Then the shortest path, so suppose this is S, this is say C, B, D, so this is actually A, B, C, D, E, F, say this is G. Now shortest path to C from the source vertex S is what? You can see there are two paths, S, B, C, there is one path. The length of this path is 10.6. So length of, so L, S, B, C is 10.6. There is another path S, D, C whose length is 5.3. So we will say, and there are only these two paths. So we will say the shortest path from S to C, which will denote the length as delta SC is actually the minimum of the two, which is 5.3. So the shortest path to B from S actually is 4.5. To C is through this and this, and shortest path to D is actually this. Shortest path to E is this. Shortest path to F is this, and shortest path to G is this. So what the double lines will tell you the shortest paths to all other vertices. I think this is the right one. So this is the right one. So this is the shortest paths to all other vertices. And now we should look that there is a property of all these paths. The graph which is made by all these paths is what? It's a tree. It's a tree. Somebody told me that it's a minimum spanning tree. It's not true. Maybe in this case I have not verified, but in general minimum spanning tree is not the shortest path tree. Don't make that mistake. Shortest path tree is different from minimum spanning tree. But this is a tree, that's the first thing. So if we compute all the shortest paths from the source to all of the vertices, they form a tree. That is called the shortest path tree. Okay, how do we prove that there is no, why this should be a tree? You know, to prove that it is a tree, what we have to show? We have to show there is no cycle. So suppose there is a cycle. So I start from S and say to the node V there is a cycle. How can it happen? There is a path. There are two paths to V. Suppose this is the most general case. So suppose say through C and D there are two paths. One is this way, another is this way. Suppose there are two paths to V. Then we will argue that either these two paths have equal weights, or one path has weight than the other. If one path says this one has less weight than this other one, then the shortest path cannot have this particular path here. So if the both paths do not have the equal weights, you will choose only the path which has the less weight. That is by definition. And in case both paths have the same weight, in that case we will see, or we will say that we will choose only one path, because we are required to choose only one path, shortest path to a vertex. So in that case also you don't have this cycle. So this means there is no cycle which implies shortest path graph is a tree. So we are precisely required to compute a shortest path tree. So now let us see what is the algorithm for computing it. So the algorithm, so this is the Dijkstra's algorithm. What I will first tell you, what is the rule for Dijkstra's algorithm. So for the time being you believe that the algorithm works. Why it works? It requires a proof. So the method is this. I am going to write starting from the source vertex S, we grow, again we grow the shortest path tree, just like in Prim's algorithm. You remember we grew one tree to a full spanning tree. Here also we start from the source vertex S and we start growing the tree to a full spanning tree. We grow a shortest path tree. So shortest path I will denote SP. So SP tree, and gradually expand it or incrementally expand it. Okay, what is the rule? This is the invariant for all vertices V that are not yet in the tree. We maintain a priority value, p value, that reflects, what is this p value? It is the length of the path from S to V using only the vertices in the tree except V. So if you first read this statement, then I will also explain what it means. So from this onwards, so for all vertices V, again we will maintain a priority value. What is that priority value? It is saying what is the priority value. Since we are growing a tree, at any point of time you have a set of vertices which are already included in the shortest path tree. You are slowly including more and more vertices, just like a Prim's algorithm. So at any point of time you have a set of vertices which are included in the tree. For those ones which are not in the tree, the weight of that vertex is basically the length of the shortest path to that vertex from the source among all the paths that are going only through the vertices which are already included. So this is most important. This is the most important thing. That is the last statement. S to V using only the vertices in the tree except V. So your tree is growing. So at any point of time, some part of the tree has been grown. So for all the vertices which are not yet part of the tree, you maintain the weight. What is that weight? It is the shortest path to that vertex among all the paths that are using only the vertices which have been already included. So pictorially it means this. So suppose I have this set, say S, and this set say V minus S, which had not been yet included. So S is the set which have been included so far, all vertices. So suppose I have a vertex say W here. What will be the W dot P? That is the priority. It is so so there are several paths. So this is the source vertex. There are several paths going to V. So there are several paths which all the paths have all the vertices inside this set S except the last vertex. So this is an H. So among such paths, the path which has the least weight, you put that one as the priority for that vertex W. But actual don't get confused. The actual shortest path may be something like this, which may include some vertices from S, some other vertices from V minus S. But we are not talking about that one here. We are maintaining the weights only the shortest among all these paths. And Dijkstra's algorithm says every time you choose the vertex with the least weight, and it is correct. Among all the weights, if you choose the vertex with the least weight, that is the correct vertex to include this time. That will give you the correct shortest path to that vertex. So can you see the similarity between Prim's and Dijkstra's algorithm? Dijkstra also maintained S and V minus S. It also maintained the weights. It also took the least weight. But only thing is this time the weight is different. Previously weight was something else. Here weight is only different. But all the other operations are almost equal. Same. So if you have understood this strategy, now I am going to write down the algorithm. The formal algorithm I am going to write down. It will be very similar. So here is the algorithm. First is the initialization. So this is the algorithm. So initialize, again we will maintain a priority queue. PQ initially is empty. Then for I is equal to 1 to n, do if I is not equal to k, then you remember what is I not equal to k? Basically this k is the index of the vertex which is taken as the source vertex. So if it is a source vertex, we put that priority a little bit differently. So I not equal to k, then Vi dot p should be infinity. It should not be chosen. Else, just like the previous algorithm, else Vi dot p, that is Vk dot p, it will be 0, and Vi dot pi. Again we will maintain the path. Pi field will give you through which edge that particular vertex has been reached, so that you can reconstruct the tree. Vi dot pi is equal to nil, and that is end if, and then add I with priority Vi dot p to the priority queue PQ, and this is end for. So this is our initialization. Initialization is not doing anything great here. So basically it's just very similar to the Prim's algorithm initialization. So you take k as the start vertex, the source vertex. Only for that vertex its priority is 0 and its path is assigned to nil. For all other vertices the priority is infinity. And with this priority you insert all these vertices in a priority queue. So this is the initialization. Now comes the algorithm. So here is the algorithm, actual algorithm. While we will take out vertices one by one from the priority queue. While priority queue is not empty, do I is equal to extract mean priority queue, you just extract the minimum one, then you get the link list associated or the adjacency list associated with this vertex I, because you need to go over that list. So T is equal to Vi dot adj, while T is not equal to nil, do j is equal to T dot V. So this will give you the index of the vertices which are neighbor of I basically. So you are going through this list. If j belongs to PQ, you have to remember whether j is already in the set or not. That is checked by here. If j belongs to PQ, and what is the weight? How do you calculate the weight? Vi dot P plus Wij. So Vi dot P. So you are going to include ith vertex. So when you include the ith vertex in the set S, you have to update weights of all the other vertices which are neighbor to it, because their weights may be changed by including I in the set S, and that's what it is doing. If this is less than equal to Vi dot P, then you Vj dot P, sorry. If it is less than equal to Vj dot P, then delta is equal to Vj dot P minus Vi dot P plus Wij. So you just take the difference, that is the delta, and decrease key in the priority queue for the vertex j delta amount, the weight of vertex j by delta amount. And not only that, you assign Vj dot pi. So Vj dot pi is equal to I. You are, in this case, you are going, if you choose j at some point of time, you have reached j through I. You are just recording that fact. And this is the end if T is equal to T dot next end while and end while. So that's the algorithm. So that is the entire algorithm for Dijkstra's shortest path. So I hope you have understood it. So this, let me go over it a little bit slowly now. What we are doing, you are extracting the vertex from the priority queue with the minimum weight, and I already told you the vertex with the minimum weight will be the correct vertex to include this time. This weight will give you the correct shortest path weight from the source to I. When you include I, what you need to do, since previously I was not there in the set S, the weights of its neighbor were different, may be different, because you have included the vertex I into the set S, it might change the weights of its neighbors, because for its neighbor the paths now may include I. Previously it were not allowed. Previously I was outside the set S, so all the shortest paths could not have included I on it. But now suddenly I is going to be included in the set S, so you need to compute the shortest path which include I on it to all the vertices which are neighbors to I. So that's what you are doing, checking all the neighbors in this while loop of I, and checking any of the edge weights will be less, any of the weights for its neighbor will be less if there is a shortest path through I. So if there is a shortest path, what it should be? It should go over up to I, that is Vi dot P. Already Vi dot P records that weight, plus Wij, that is the edge from I to j. If it is less than already recorded value of the j, then you should update it. That's what this one is doing. So pictorially it means your set is S here, you are going to include I here. So you have included in this step I here. So your J is outside here. So now, so suppose this is the source S. So S, I am going to include I and then I to J. So there this new path previously was not computed because I was outside. But since we have included I, this new path can be considered for J. So what is the weight of this path? This is the shortest path to I, which is Vi dot P plus Wij. So this is the weight of the shortest path to J which goes through I. If this is less than, then already probably you have computed something else to J, that is the Vj dot P. If this is less than this, then you should update its weight, and that's what it is doing. You take the difference of these two weights and decrease key the value of the weights for J, and you go on doing it until unless you are done with the priority queue. Yes, there is a question somewhere. Okay. So this is very similar to Prim's algorithm. If you check, only the difference is only here. Difference is only here. How you calculate the age, calculate the weights. Previously, calculating the weight, you are only taking a Wij. Now you are adding something. That's it. But you get totally different problem. You can solve a totally different problem. So this is the Dijkstra's algorithm. So why is it called greedy? It is called greedy because you are maintaining the set S and the rest of the set V minus S. You are choosing from the V minus 1 S the least one. It's akin to a greedy strategy. That's the very natural choice. I will choose the next one which is the least because we are trying to find out the shortest path, and in this case it works. This strategy works. It requires a proof, but we will see that one later. So let me go over this algorithm on an example so that we know what is happening. So let us consider the similar graph. So suppose this is S, source vertex S, 2, 6, 5, 3. So let me put this. So this is say 9.7, 1.1, 2.1. Say this is 3.5, 10.0 I guess, 1.2, 2.1. So these are the edge weights, and say this is the vertex 1, 1, 2, 3. This is the fourth vertex, 5, 6. So suppose this is the graph. So here I am showing the steps in a matrix form. So this is 1, 2, 3, 4, 5, 6, and we will see how the priorities changes. So initially what is the stage? You have chosen only the vertex 1, that is your initialization. So you have chosen vertex 1, and what are the edge weights? The weights of the vertices, 1 has weight 0, all the others have infinity, everything else has weight infinity. So the next step, from the priority queue 1 will be extracted, right? When 1 is extracted, so here minimum is basically 0 weight. So when 1 is extracted, its neighbor will get updated. It has two neighbors, 3 and 2. So 2 has edge weight 9.7. So 9.7 is less than infinity. So 2 will be updated to 9.7 and 3 will also be updated to 2.1 and all the others remain infinity. So now next time you will choose 3. So mean is in this case is 2.1. So you will choose the vertex 3. So the next thing will be you have 1 here and you have chosen 3 with the edge weight 2.1. So this is your tree at this point. So when you choose 3, you will update edge weights of 5 and 4. Weights of 5 and 4, these are the two neighbors of 3. So this one will 2 will remain 9.7, 3 has been chosen and 4 will be updated to 12.1, 12.1, 5 will be updated to 3.3 and 6 will remain as it is. Now among this one, next one will be minimum will be the node 5. So mean will be 3.3 and 5 will be extracted. So how does this tree look like now? So the next step is this is 1, this is 3 and from 3 we will get 5. So this is 2.1, this will be 1.2. So when 3 is extracted, sorry, the 5 is extracted, then it has neighbors 4 and 6. It has also neighbors 3, but 3 has already been included. You would not check it for because it does not belong to PQ anymore. That's the first check. So you will update 4 and 6. Now look at 4. What is happening? So 2 remains as it is. Say 9.7. 2 remains as it is because it is not affected. 3 has been extracted. Now look at 4. 4. What is 5? What is the priority of 5? Priority of 5 was 3.3 and 3.3 plus 3.5 it will be 6.8. Now 6.8 is less than 12.1, so it will be updated. So 4 will get updated to 6.8 and here what something is interesting is happening. Your previously shortest path tree was something like this and 4 was basically had a pi field which was belonging to 3 previously, but since now you have got a better path through 5, you are going to update this link. So now the link is 4 will link to 5, not anymore to 3, because you have got a new path which is better, and that's why you need to check all the neighbors of a vertex when you include that vertex into the set S. That is the main part of the algorithm. When you have included vertex 5, you have found a new path to other vertex which is better. Previously you could not see this path because that path did not exist previously to the vertices of S. So this 12.1 gets updated to 6.8, 5 have been extracted. Now 6 will get updated to 5.4. So the next minimum is 5.4. So 6 will be extracted. So this will look like 3, 5 and then 6. So this is 2.1, 1.2, 2.1. So 6 will be extracted. When you extract 6, again something interesting happens, I guess. It has two neighbors, 5 which has been already included, but it has a neighbor 2 which has not been included yet. And 2, have you got a new path which is better? 6 has already 5.4, 5.4 plus 1.1, 6.5. So 6.5 is much better than 9.7. So this will be updated to 6.5. So look at this. Previously from source vertex to 2 there was a single edge path, but that was large 9.7. But here now you have got a better path going around all the vertices, but it is a better path now. So you would update this path. So 2 will be 6.5. This is extracted. 4 remains 6.8. This is extracted. 6 is extracted. So the next step, minimum is 6.5. That will be 2 will be extracted. So if I extract 2, how does it look like? So this is 3, this is 5. All the time you can see we are maintaining the tree so far. 5, now 6, and 2. So this is 2.1, 1.2, 2.1, 1.1. And when you extract this vertex 2, you can only update 4 which has not yet been extracted, but that cannot be updated. So 2 has been extracted, 4 remains 6.8, everything else has been extracted. So next time what will be your mean? Mean is 6.8, and you will get basically the other final tree somewhere here, which is basically it will join 4 here. So it will be 3.5. So you will get the entire shortest path now. So this is the, so you starting from the source vertex S, this is the tree you will get. You can see this is a tree. This is a tree because this is a connected graph, no cycle. And what any vertex you go in the tree, it will give you the shortest path in the graph. Between any two vertices of a tree, there is a unique path, and that path will give you the shortest path this time. So this is the Dijkstra's algorithm, how it works. Now let us see what is the complexity of this algorithm. Again, how much time does it take? It depends how we implement again the priority queue PQ. If PQ is implemented as a heap, if PQ is implemented as heap, how much time does this take? Order. If it is a heap, so total this while loop is will be executed. Order. How much time is that? While loop will be executed how much? Order. Order m, where m is the number of edges. The total while loop execution will be order m, and this one will be executed how many times? This while loop will be n times. Now this is total m, and each m involves one decrease key operation, and there is an extract mean operation per vertex. So extract mean will take how much time? N vertices, n log n. And this decrease key per edge, there are total m edges you have to do. Decrease key, suppose you are doing a heap, normal heap, that will give you m log n. So basically you have n log n plus m log n if normal heap. But if you use a Fibonacci heap, then suddenly this decrease key is an order 1 operation in the amortized sense. So order 1 operation in amortized sense, you are doing m operations, order m operations. So that will take order m time. So total complexity in that case will be m plus n log n. Okay, if you use Fib heap. These are the two time complexities of this algorithm. So basically they have, this has the same time complexity as the Prim's algorithm. Now there is another version of this problem. That version is called, so this time only a single source was specified and you were supposed to find out the shortest path to all other vertices. So in the other one, we will be required to find out shortest path between any pair of vertices of the graph. So if there are n vertices, so n choose 2 pairs are there, you are required to find out shortest path between any such pair. So that problem is called all pairs shortest path problem. So in this problem, we are required to find shortest path between any pair of vertices. Now let's see. Suppose you don't know anything else now. What is the best algorithm you can provide for this problem? For each vertex, you can take it as a shortest path source and run Dijkstra's algorithm. So if you do that, you will get shortest path between any pair. So how much time does this take? Mn plus n square log n. So this will be if Dijkstra is invoked for each vertex. But you can see in the worst case how much time does it take? When m is equal to n square, it will be n cube. So in the worst case, this will give you an n cube algorithm. By the way, for this particular problem, you cannot avoid, what is the time complexity you cannot avoid? You cannot go below what? You cannot go below at least n square, because the n square paths are there. You cannot go below n square. So it will be any algorithm you devise for this problem, it will have a time complexity more than n square. Okay. There is another method which we will study, which will take n cube log n time. This will be done by matrix multiplication. And third will be n cube, so all are order. This will be given by Floyd-Warshall's algorithm. Okay, why all these three? Definitely n cube log n is not better than this mn plus n square log n. Even n cube is not better than this naive Dijkstra running for n vertices. Then why somebody has invented this particular order n cube algorithm? This is because Dijkstra's algorithm only works for graphs without any negative cycle. What do we mean by negative cycle? There should not exist any cycle in the graph whose weight is negative. If such negative weight cycle exists, Dijkstra's algorithm does not work. You should go and verify this statement. You should take a graph with a negative weight cycle and check why Dijkstra's algorithm is not working. If you run the Dijkstra algorithm on such a graph, you will see it will make a wrong choice. So to be safe, Dijkstra's algorithm only works for graphs with positive edge weights. It also works for graphs with negative weights, but in that case the negative weight should not make a cycle. You cannot find a cycle in which if you add the weights of the edges on the cycle, that should not add up to a negative number. If it does, Dijkstra may not work. So to tackle all these graphs, we have these two algorithms, second and third. So this algorithm can take care of all negativity and everything, and definitely this is much better than this. That's why this is invented. So in the next lecture we will see how this second one works, and then in another lecture we will see how this fluid washers work.